Okay, we're going to start notes for particle motion, and then we can also go back and review power rule today as well. So if you have to turn to page 27. So we've learned about first derivative. We know first derivative is just representing rate of change or slope of the original function. But we can also talk about derivative from other contexts, context of position and velocity and acceleration. So this feels maybe more just more something that we can relate to them that feels more more like real world application. So instantaneous velocity of the object is the derivative of the position function with respect to time. So if we let S of t represent position, so think of your position function as your original function. Gives you the position of the object at any moment in time. And then so the derivative would be velocity. Velocity would indicate the rate of change of position with respect to time. And we can think of velocity is simply just the derivative of position. So we take S prime of t, that will get us to the velocity level. And acceleration is the derivative or rate of change of velocity. So the change in velocity over time is acceleration. So we can think of acceleration as the second derivative of position. We can also think of acceleration as the first derivative of velocity. And we can also have acceleration have its own variable a of t. Okay, so depending on where you start from, if you're starting at position to get to acceleration, you have to go down 2 levels. But if you're starting at velocity to get to acceleration, you only have to go down 1 level to get to acceleration. So there's average velocity or average rate of change and also instantaneous rate of change. If you see average rate of change, that means there's no calculus involved. It is just slope. And slope is just finding 2 points and doing change in y over change in x. If you see instantaneous rate of change, then it's asking what is the exact velocity, exact rate of change at that moment in time. And because of that, we will have to do calculus for that. So if you see instantaneous rate of change, then this is where we have to find the derivative and use calculus. See, use derivative. Okay, so speed is related to velocity. Speed is the absolute value of velocity. So velocity has direction. So you can have positive velocity, you can have negative velocity. Usually that indicates which direction the object is going. So velocity can be positive, could be going up, positive velocity. Negative velocity could be how fast the object is going downward. But speed is always positive, right? You could be going up, you could be going down. It's always the positive version of velocity. Okay, displacement is how far you are from where you started, and distance is the total amount you have traveled. So if you have a lot of, if the object goes back and forth, we're counting all of those as positive values. So example, if I travel 10 feet to the right and turn around and travel 3 feet back, my distance is 13 feet, but my displacement is 7 feet. Because if I travel to the right and if I travel back 3 feet, the forward progress that I made is only 7 feet. But my distance is 13 feet because we took, in this case, let's say you do one step is 1 foot. So this person would, or this, I would travel, I would take 13 steps. So 13 steps is the distance, but displacement is how much progress you've made from your starting point to your ending point. Okay, we're going to review this a lot here. This is going to come back in quite a bit. The idea that speed is increasing when velocity and acceleration have the same signs, but speed is decreasing when velocity and acceleration have opposite signs. Now, what's related to position, velocity, acceleration is particle motion. Particle motion is specifically for linear motion. So this is when an object is moving along a line, usually a horizontal line, going back and forth. So if we ever talked about particle motion, it's basically linear motion. So we're talking about, that this object is either staying still, is moving to the right, or is moving to the left. And those are the only 3 things that this object can do. So a positive, so sometimes we use, instead of S, there's a lot of different variations of position function. You may see S of t to represent position. You may also see X of t to represent position. And X of t usually indicates that this object is moving along the x-axis. And we're asking for the position of that particle along the x-axis. But then the V in velocity acceleration still maintains the same letters, but it's position that can change its letters depending on the context. So a positive velocity would indicate that the particle is moving in the positive direction. And it's usually going to be to the right. Negative velocity indicates that the particle is moving in the negative direction, and that's usually to the left. And then when velocity is equal to 0, that's when the particle is at rest. stage. Okay, a ball is thrown vertically upward from the edge of a building and it eventually hits the ground next to the building. If the height of the ball at any given time is h of t, answer the following. So h of t will tell us at any moment in time how far is the ball off the ground, or how high is the ball off the ground. So just to kind of give a, let's say this is the edge of a building here, and the ball is being thrown upward, and then eventually it's going to hit a peak, and it's eventually going to come down and hit the ground. Zoom in. Okay, so how tall is the building? So we know that the ball is going to start off at the top of the building at 0 seconds. So if I plug 0 in, I can find out the location of the ball, which is also the height of the building as well. So we can say h of 0. Remember, any t value I give it in return is going to give me the height or the position of the ball, which happens to also be at the top of the building. So because the ball is starting at the top of the building at 0 seconds, we know that is also the height of the building, 80 feet. Because we know we're going to involve velocity and acceleration, let's go ahead and find each of those functions, and they're just derivatives of each other. So you can already see that we have all these different variations of position function. It can be s of t, it can be p of t, it could be h of t, it could be x of t. So all these different variations that all represent position in one from different contexts. So I'm going to write out the position function over here. Let's just go ahead and gather all of our derivatives. So I'm going to say h prime, which is going to be velocity. So what's the derivative of each of these terms, which will give me the velocity function? Negative 16t squared becomes what? Good. Negative 32t plus, what does 64t become? Guess what? Just 64, right? So if you imagine that this is just a linear graph, if I ask you, y equals mx plus b, if it's a linear variable, if it's a variable to the first degree, then whatever's in front is the slope, right? And the slope is derivative. So if you have a linear graph, that t just goes away. I'm just left with 64. What happens to the constant? 0. Good. So every degree drops by 1. So degree 2 goes down to degree 1. Degree 1 goes down to degree 0. And there's no degree, that constant just goes away to 0. So let's go ahead and find the acceleration function, which is another derivative down. So what's the derivative of negative 32t? Guess what? Negative 32, yeah. And then the 64 goes to a 0. So let me talk about each of these functions in terms of what it does. Here, these are all t values. These are all moments. These are all seconds. So if I plug in 2 seconds or 3 seconds or 4 seconds into the position function or height function, it'll give me the location of the ball, how high it is off the ground. If I plug in the 2 or 3 or 5 or 0 into the velocity function, guess what it's going to give me in return? Give me the velocity value, right? How fast the ball is moving and in what direction. If it's a positive velocity, it means it's going up. If it's negative velocity, it means it's going down. And acceleration is always -32 because that's acceleration due to gravity. So it's always a constant force because of gravity. So that acceleration never changes. So let's look at number 3 here. When does the ball reach maximum height? So if we think about this ball's movement here, initially this ball is going to have positive velocity, but what's going to happen when it reaches its peak? Momentarily, the ball is going to have what? A velocity of 0, right? If you throw it straight up, then it's going to have this momentary, this moment when it's not going to be moving at all because it's going to eventually make its way down, right? So we know the ball is going to reach the maximum height when velocity is equal to what? 0. Yeah. Not for every problem, but for the context of this problem, it makes sense because the ball is just going to stop momentarily, reaches maximum height before it starts going down. So then we can figure out when by solving for t. So I can plug 0 in for what? Do I plug 0 in for t or 0 in for the v of t? V of t, yeah, because I know what velocity I have, but I'm asking the velocity function, what time did I achieve the velocity of 0? So I can plug 0 in for v of t and then solve for t. And then solve for t here. 32t equals 64. So t is equal to what? Yeah, 64 divided by 32, 2 seconds. So we know that after the ball is thrown up in the air from the top of the building, 2 seconds later, it's going to reach its maximum height. And after 2 seconds, it's going to start to make its way down to the ground. So now, next question is, what is the maximum height? We want to find maximum height, so we got to use the position or the height function. What can we plug in for t to find the maximum height? 2, right? Because we know how long it took to get to the top of it, to get to the peak. So we can just plug 2 into the height position function and figure out how what is the height of the ball 2 seconds after the ball was thrown. So these are larger numbers, so I'll do the math for us. So it ends up giving us 144 feet if we plug into the function. So 2 seconds after the ball was thrown up in the air, the ball is going to be 144 feet up in the air. Next up, how long does it take to hit the ground? So let's think about position here. When the ball hits the ground, what is the height of the ball? 0. So I could just set h of t equal to 0 and then solve for t, right? I know what position, I know what height I want because it's on the ground, which is 0, and I can work backwards and solve for t to figure out at what time is the ball going to hit the ground. So I set height equal to 0. This is something that we can factor. This is trinomial factoring, but we always want to start off with GCF. So I can factor out a -16. 64 divided by 16 is, or 64 divided by -16 is -4. And then 16 times 5 is 80. So we can continue factoring t squared minus 4t minus 5. Both sides to be -5, adds up to be -4. It's going to be -5 and 1. And now we can solve for t. If you see a value with no variable in it, that means there's not going to be any solution here. I mean, if we set negative 16 equal to 0, there's nothing to solve. But we can solve for t and solve for t minus 5 and solve for t plus 1. So what t values do we get? T equals what? 5 and -1, right? But -1 is not going to make sense for the context of this problem because we're only talking about time after the ball is thrown, not time before the ball is thrown. So only 5 seconds makes sense. But graphically, this kind of makes sense because this is a parabola here. And if we follow the path of the parabola, it will eventually hit the x-axis down here. And because of that, that's where that -1. So basically, this parabola has an x-intercept at -1 and 5. But for the context of this problem, we're starting in the middle of the parabola here. So only positive 5 makes sense. So then we can say 5 seconds after the ball is thrown, the ball is going to hit the ground. Okay, next up, what was the initial velocity? So what does that word mean? What does initial mean? That means the beginning, right? So beginning, that means when t is equal to what? What's initial? 0, right? That's the very start of our problem. So guess what we can do if we want to find initial velocity? Plug 0 in for t of my velocity function, right? Now I'm going to be asking for your units of measure as well on the quiz. So what's our units of measure for velocity? Feet per second, yeah. So we can say feet per second. Okay. What's the velocity at 1 second? What's the velocity at 2 seconds? We can use the same velocity function and find out the exact velocity at those moments in time because we can use our velocity function. We can do calculus. We can use our calculus function because we're asking for a specific moment's velocity. So v of 1, plug 1 into the velocity function, you still get 32 feet per second. V of 2, we know it's going to be 0, right? Because this is when the ball is at its peak and momentarily it's not moving. Okay, so these are pretty straightforward, right? We're just plugging t values into the function. What's the height at 3 seconds? Same idea, just plug 3 into the position function. Number 9, what is the speed when the ball hits the ground? Now, we know speed is related to what? Velocity, yeah. So let's just worry about velocity first, and then we can deal with the speed later. So let's find the velocity when the ball hits the ground. Now, do we know how long it takes for the ball to hit the ground? What did we discover before? 5 seconds, right? So now we can find the velocity at 5 seconds because we know how long it took to hit the ground. So we'll do v of 5. Now, what do you expect from velocity? Which direction is the ball going when it hits the ground? Down, right? So we expect a negative velocity. So let's just plug 5 in and see what we get. So negative 32 times 5 plus 64 equals negative 96 feet per second. Now that's the velocity, right? Because the velocity at direction, that negative tells us that it's um, moving towards the ground at 96 feet per second. But if we want speed, we just change that to a what? Positive, yeah. So speed is always positive. So speed is 96 feet per second. Now, if velocity is already positive, then your speed will be the same number. So your speed and velocity will not be any different from each other if velocity is already positive. But if velocity is negative, then the speed is going to make that change to a positive. Okay, what about acceleration? Is acceleration ever changing? It's always remaining at negative 32, right? So I can plug in 1, I can plug in 2. It's always going to maintain the same. Not in every case. It's only when for problems where you're throwing a ball up in the air. But if it's a particle motion problem, your AFT may have variables in it. If it does, then you got to plug in and find that acceleration. So we can say A of 1 is equal to negative 32. And what's our unit of measure for acceleration? Feet per second. Yes, it's feet per second per second. It's the rate of change of velocity. So velocity is feet per second, and then you're dividing by seconds. So we can say feet per second squared. Same thing. A of 2 is also negative 32 feet per second squared. All right, put a star next to these 4. These are the ones that are going to be more difficult. Well, be more difficult because because it's easy to misinterpret. Okay, it says find the average velocity on the interval from 0 to 2. There is a word here that makes this tricky. What is the word that we have to be careful about here? That word average. That average throws it off because we may be focusing on the word velocity, which is the velocity function, but it's actually for the average velocity, which means it's not, which when we talked about whenever we see average velocity, there's no calculus involved. Okay, so what I mean by no calculus is that we're not going to be involving the velocity function, which came from position. Okay? We're going to purely use the position function. Okay? Because the way we define average velocity is change in position divided by the change in time. So we don't use velocity function at all to find average velocity. That seems kind of strange, but that's the way we define it. So we basically have to find the position of this particle, of this object, the ball at 2 seconds, find the object's position at 0 seconds, and then just find the slope or the rate of change between those 2 points. So we'll find h of 0, which we know is 80, right? We'll find h of 2, which from before is 144. We just want to find out over the 2-second interval, what is the average velocity? So average velocity is just 144 minus 80 divided by 2 minus 0. And that just becomes 32 feet per second. A lot of things that students want to do incorrectly here is find the velocity function at 0 and 2 seconds, and then either do slope between those two or find the average of those two numbers. But the reason why this is so troublesome for students is because you see that word velocity and it's naturally feel like, well, if I see velocity, I'm going to use velocity. But that average throws everything off. Now, if it's asking for instantaneous velocity, or if it just says find the velocity at a moment in time, then you use calculus. But if it's find the average, if you find the velocity over a time period, then you just rely on position function. You don't use velocity function. So number 12, same idea, find the average acceleration. Again, this word is throwing us off, right? Because we see acceleration, but there's the average in front of it. So guess how we define average acceleration? It's defined as what? Change in velocity over the change in time. So we're not going to use acceleration if we see average acceleration. We're going to use what? Use the velocity function. So we need to find the velocity at 1 second, find the velocity at 2 seconds, and just simply find the slope between those 2 points. Okay, so V of 1 is 32. V of 2 is 0. So my average acceleration is just V of 2 minus V of 1 over 2 minus 1, which is 32. Oh, sorry, 0 minus 32. Over 2 minus 1, which is negative 32. Now, even though we never touch the velocity function, we're still asking for, even though we never touch the acceleration function, we're still asking for something that is referencing acceleration. So our unit is still going to be feet per second squared. Is the speed increasing or decreasing at t equals 1 second? So we talked about how if we want to do increasing, decreasing speed, we're going to be comparing the signs between velocity and acceleration. If the velocity and acceleration have the same signs, then speed is increasing. If velocity and acceleration have different signs, then speed is decreasing. So if one is positive, the other is negative, my speed is decreasing. But if they're both positive or they're both negative, then my speed is increasing. So we got to compare signs, right? So V of 1 is 32. A of 1 is negative 32. So what can we conclude? Speed is decreasing because one is positive and the other is negative. So we can say speed is decreasing at t equals 1. As V of t and A of t have opposite signs. This one is actually a bit more straightforward. Number 13 is straightforward because it follows the rule that we learned on the previous page. Number 14, though, is tricky because it says, is the velocity increasing or decreasing at t equals 3 seconds? We see the word velocity, but is this talking about velocity? What do you think this is talking about? The word is increasing, decreasing. What do you think that's talking about? So here are the options. Is it talking about position? Is it talking about velocity? Is it talking about acceleration? Is it talking about speed? Yes, right. Okay, it's actually acceleration. You know why? You see that word increase, decrease? This is another way of saying the rate of change. So if we're talking about rate of change of velocity, that means we're down at the acceleration level. And AP College Board, they love to do that. They love to use these words to change the meaning of what's going on and see if students can catch on to that. So velocity increase, this is talking about the rate of change of velocity, which is really acceleration. So it'd be a lot simpler if the problem just says, is acceleration positive or negative at 3 seconds? But the wording that you're going to get is the velocity increasing, decreasing at 3 seconds? So since we know that this is not talking about velocity, it's talking about acceleration, we can find the acceleration at 3 seconds, which we know acceleration is always going to be what? Negative 32 feet per second squared. And because it's negative, we know that velocity is decreasing. So velocity is decreasing because acceleration is negative, but if velocity was increasing, then acceleration would have to be positive. Okay, let's go to page page 29. Let me run through a few things with you here. So page 29, number 4. It says, if a particle moves along a line according to the equation s of t equals t to the 5th minus 5 to the 4th. So we know that this object is moving left and right, and at any given time, it'll tell you where the particle is on that line, on that x-axis. How many times does a particle reverse direction? So if we're talking about reverse direction, that means it's moving left, then suddenly it's moving right. But in order for an object to reverse direction, what does the object have to do before it can change direction? The velocity has to be what before it can change direction? Zero, right? Because if it's moving left and right, he's got to stop momentarily in order to change direction, right? So anytime we're asking for a change in direction, we have to first figure out the candidates. So we have to figure out when is the velocity 0, and then we can see if there's actually a change in signs on either side of our number line. So we're going to create a number line for this. So first, let's build a velocity function, because reverse direction is when velocity, well, first we got to figure out when velocity is 0. So v of t is equal to, what's the derivative to get to the velocity function? T to the 5th becomes 5t to the 4th, right? And then what's 5t to the 4th become? What's the derivative? 20t to the 3rd, yeah. So we talked about a prerequisite for reversing direction. It's got to be motionless. So let's set velocity equal to 0, and we can factor out the t. We can factor out 5t cubed, and we're left with t minus 4. We solve for t. We have two places where t shows up. We set that equal to 0. We set that equal to 0. We get t equals 0, and we get t is equal to 4. Now, they don't give us a restriction that time is only positive. So if they don't give us a restriction, we just assume that then it's all real numbers. So we can have negative t values, we can have positive t values. So we're going to create a velocity sign line, a number line, and we'll put 0 and 4 on that number line. So this tells us that in each of these regions, this object is only moving in the same direction, either left or right. So there's not going to be a sudden, because he's only going to be either moving left or right in this region. He's only moving left or right in this region, only left or right in this region. The only breaks that we can have is at 0 and 4. Okay, so all we need to do is to find one number to test, because once we can find the behavior at that moment in time, it's going to be consistently the same direction of motion for that entirety of that interval. So I like to choose numbers that's closest to 0, because those are easy numbers to plug in. I'm going to test -1, I'll test 1, and I'll test 5. Those are just the smallest numbers that I can find in those intervals. So I'm going to plug -1 into my velocity function. I don't care about the velocity value, I just care about the sign. So if I plug -1 in for t, what do I get here? Positive or negative? Negative. If I plug t in here, sorry, if I plug -1 in here, I also get negative. Two negatives makes what? Positive. So that means in this interval, my object is moving to the right. I'll do positive to indicate it's moving to the right. Okay, next up, let's plug 1 in. If I plug 1 in for t, again, I can plug into the original velocity function, which is fine, but I like to put into factor form because I can just gather my signs and see how many positive and negatives I get, and then decide what the sign is. So if I plug 1 in for t, what do I get? Positive or negative? Positive, okay. And then 1 in for t here. Positive and negative makes negative, so I know that there's a change in direction there. And then if I plug 5 in, what do I get? Positive and positive, so positive, positive. Now, we're gonna do a lot of these number lines over the course of this unit, next unit. But one thing I want to make sure that we know is that once we test our numbers, we don't care about those numbers. We're not going to use those again in our interval. So as soon as you find, we're only using those numbers to figure out the plus and minus. So after that, cross them out because we're not going to use them. Never use those numbers when you're creating your statement. It says how many times does the particle change direction? Only what? Twice, yeah. And let's say, let me extend the problem a little bit and say, when does a particle move to the left? So we can say moving left on the interval from where to where? Assuming negative is left, 0 to 4, yeah. So left when 0 to 4. And then moving right when we have two intervals, right? The arrow this extends all the way to where? Yeah, so negative infinity to 0, and then comma or union, and then pick up again from 4 to infinity. So again, notice that we never touch the -1, 1, and 5 in our statement. The statement is based off of what you put in, originally on your number line, which are just the critical points. Okay, so your homework, it says page 28 to 32, but we're just going to do page 29, sorry, 30, 31, and 32. I'll send out a reminder on Sunday and also send you, well, I'll put the link under today's date on my website so you can check your answers. But page 30, 31, and 32. Homework over the weekend, but I'll send out a reminder on Sunday since it's over a weekend. And then Monday, we'll do product rule and quotient rule. And then we'll do quiz review. And we'll just start the next section on chain rule. It's not going to be on the quiz, but it kind of buys us another day to review. And then your quiz is next Thursday. Okay. I'm pretty much done with grading your limit test, so I'll put that in the gradebook this weekend and give it back to you on Monday. All right, come in front. Okay. Then you can show me the.
I showed you the AP questions.
Right. Right. And then the for AP. Thank you.